Good morning. We have already learned that, when viewed at a local level, the gravitational field near the surface of a planet has a uniform magnitude and is directed downward toward the center of the planet. We have also learned that the electric field which exists between two parallel plates of uniform opposite charge also has a uniform magnitude and is directed from the positively charged plate to the negatively charged plate. However, we have never really shown where that electric field came from. Today, we are going to do exactly that.
Flippin' physics!
Let's start with two parallel plates made of a conducting material. And let's give the top plate a net positive charge and the bottom plate a net negative charge. Both plates are in electrostatic equilibrium. This means the charges in both plates are not moving and have arranged themselves to be uniformly distributed throughout the plates. Now, before we do anything else, I want to clarify that our whole discussion here is going to be about an ideal pair of parallel plates. An ideal pair of parallel plates are large enough compared to the space between the two plates that the plates themselves can be considered to be infinitely large. I have a separate video for you to watch after this if you want to learn about a non-ideal pair of parallel plates. Okay. The intent with each of these positive signs is to represent the charge of the excess protons causing a net positive charge on the top plate. And the intent with each of these negative signs is to represent the charge on the charge of the excess electrons causing a net negative charge on the bottom plate. Realize each of these charges is infinitesimally small and has a charge equal to the elementary charge. In other words, each of these charges has the same absolute value. The ones on the top plate are positive and the ones on the negative plate are negative. However, when you take their absolute value of their charge, they are equal in value. And again, they are infinitesimally small. However, I cannot make them infinitesimally small in the illustrations or you would not be able to see them. Also, even though the parallel plates appear to be one-dimensional in this illustration, like this piece of paper, they are actually two-dimensional planes oriented like this. You only see one edge of them in the illustration. Again, this sheet of paper, which I'm using to illustrate one of the parallel plates, is oriented like this and can be considered to be an infinitely large two-dimensional plane. Okay, here we go.
Here we go!
Where are we going?
Here.
Yeah.
Absolutely.
Okay. Let's place a positive test charge in the middle between the two plates and determine the direction of the net electrostatic force acting on the positive test charge from all the charges on both plates. Realize a test charge is a hypothetical positive charge with a magnitude so small that it does not alter the electric field in which it is placed. Let's start by picking just one positive charge in the top plate to the left of the center line, which I've labeled charge 1. Bobby, tell me what you know about the direction of the electrostatic force from charge 1 on the test charge.
Okay, you are looking for the direction of the electrostatic force from charge 1, which is positive, on the test charge, which is also positive. Then we know from the law of charges that two charges which are like charges repel one another. In other words, because charge 1 and the test charge are both positive charges, they repel one another. That means the direction of the electrostatic force from charge 1 on the test charge will be directed down and to the right, extending a line which goes from charge 1 to the test charge, right?
That is correct, Bobby. And notice there is a charge, which I've labeled charge 2, that is located to the right of the center line of the parallel plates, such that charge 1 and charge 2 are both located an equal horizontal distance from the center line of the parallel plates. For the same reasons Bobby just identified, the direction of the electrostatic force from charge 2 on the test charge is directed down and to the left, extending a line which goes from charge 2 to the test charge. Notice both of these forces are directed at the same angle below the horizontal. Bo, please determine the direction of the total electrostatic force on the test charge from both charge 1 and charge 2.
Sure. Well, both forces are at the same angle below the horizontal and have the same magnitude. So when we resolve those forces into their components in the x and y directions, you can see the component of force 1 in the x direction is to the right, and the component of force 2 in the x direction is to the left. Because both forces are equal in magnitude and their angles are the same, their x components will also be equal in magnitude. Because they are also opposite in direction, their components in the x direction cancel one another out. So the total electrostatic force from both charge 1 and charge 2 on the test charge has no component in the x direction. Both components of force 1 and force 2 in the y direction are directed toward the negative plate. So those are in the same direction and equal in magnitude. That means the total electrostatic force from charge 1 and charge 2 on the test charge is directed in the negative y direction straight toward the negative plate.
That makes sense, but how do we know both electrostatic forces are equal in magnitude?
We can use Coulomb's law to show that both electrostatic forces are equal in magnitude. Coulomb's law states that the electrostatic force equals the Coulomb constant times charge 1 times charge 2. Actually, let's call them charge A and charge B so we do not get confused with charge 1 and charge 2 on the top plate. All divided by the square of r, the distance between the centers of charge. One of the charges in each of the two equations is the test charge, and the other charge is charge 1 or charge 2. As Mr. P mentioned earlier, the absolute value of all of those charges are equal, and r, the distance each charge and the test charge are apart, is the same for both forces. That means the force from charge 1 on the test charge and the force from charge 2 on the test charge are equal in magnitude.
Right.
So we have determined that the total electrostatic force from charges 1 and 2 on the test charge is directed straight towards the negatively charged plate. Now, notice there are two similar negative charges, which I've labeled 3 and 4, which are in the negative plate, which produce the same result. This is because, from the law of charges, because charge 3 and the test charge are unlike charges, they are attracted to one another. That means the electrostatic force from charge 3 on the test charge is directed down and to the left along a line which goes from the test charge to charge 3. And you could see the same thing is true for charge 4 and the test charge, resulting in force 4, which is down and to the right along a line which goes from the test charge to charge 4. And again, those two forces are equal in magnitude. The angle with the horizontal for both forces is the same. Therefore, the components of the forces are equal in magnitude. That means the x direction components cancel one another out, and the y direction components are added to one another. The result being that the total electrostatic force from charges 3 and 4 on the test charge is directed straight down towards the negative plate. And that means the total electrostatic force from charges 1, 2, 3, and 4 on the test charge is also directed straight down towards the negative plate. And notice that for every charge to the left of the center line, there is a mirror charge to the right of the center line. In other words, the direction of the electrostatic force on the test charge is always straight towards the negatively charged plate, and as we discussed earlier, the two plates are two-dimensional planes of charges, not one-dimensional lines of charges as shown in the illustration. But realize, the argument we just used to show the direction of the electrostatic force is also applicable for a two-dimensional plane. In other words, we just showed that the direction of the electrostatic force on a positive test charge placed directly in the middle of the space between the two parallel, oppositely charged plates is toward the negatively charged plate.
That is a lot of work for just that one location.
True. However, we can extrapolate from there. For example, if we move the positive test charge closer to the positively charged plate, does everyone understand that the horizontal components of the electrostatic forces will all cancel out? And the direction of the total electrostatic force from both plates on the charge will still be straight toward the bottom plate.
Yeah, sure.
Now, the magnitude also stays the same. It is really important to realize that the only reason the magnitude of the electrostatic force on the test charge remains the same, regardless of how close the test charge is to either plate, is because both parallel plates can be considered to be infinitely large. The truth is that it takes Gauss's law and calculus to be able to prove that, which is beyond the scope of this algebra-based class.
That is too bad. But I bet you have a video about that which we can watch if we want to, right, Mr. P?
That is correct, Billy. I do. Now, Recall that the electric field is defined by a positive test charge. In other words, because the electrostatic force on a test charge would be the same no matter where it is located on the center line of the parallel plates, the electric field will have a uniform value along the center line and will be directed in the direction of the electrostatic force on the positive test charge, which is from the positively charged plate to the negatively charged plate. And to fill in the rest of the electric field, recall that we can consider the parallel plates to be infinitely large. Therefore, the electric field will have the same magnitude and direction at every location between the two plates. In other words, the ideal electric field between two parallel plates can be considered to be uniform and directed from the positively charged plate to the negatively charged plate.
Oh, that is an ideal electric field. In other words, we can consider the electric field between two parallel plates to look like that. However, that's not quite what it looks like in real life.
Like we consider objects in projectile motion to not experience a drag force, even though they actually do.
And we consider the coefficient of friction between two surfaces to be uniform, even though that is not quite true.
Okay, but what does a non-ideal electric field look like between two parallel plates?
Yeah.
Sure, that is a reasonable question, and it is also one I told y'all we would cover in a different lesson.
Oh, man.
Okay.
Of course.
Thank you very much for learning with me today. I enjoyed learning with you.